Hey folks, in lesson 13 we're going to introduce a concept that we call angular momentum, which is simply another step in which we're extending the reach of Newton's second law. So we're not using the form F equals ma any longer, at least in this chapter, but we're exploring how we can use Newton's second law, the F equals ma, to inform us about different ways to solve problems or different ways to view the motion of the system. And so let's start out with angular momentum. And this is angular momentum about a fixed point. So this is a point that's inertially fixed. And we're going to define this new term of angular momentum of mass P relative to point O, or around point O would be another way to say it, is equal to this arm, or this position vector from O to P, crossed with the angular momentum of that mass. So let's spend some time looking at these parameters that are included in the definition of angular momentum. So we often choose a fixed point, or an inertially fixed point, about which we are going to calculate angular momentum. And so this fixed point in this particular definition has to be fixed in the inertial reference frame. And so you can see here that angular momentum needs to have this superscript which tells us where we're observing that. And the reason why is because momentum itself, or linear momentum, also needs that superscript. So we have to designate both the frame of reference in which we're observing it, and then we also need to designate the point at which we're calculating the angular momentum relative to or about. So on the right hand side, it's a cross product of the position vector of mass P with respect to point O, and is crossed with the linear momentum. So the units of this angular momentum are in kilograms meters squared per second. That's really a funky units, perhaps something you haven't seen before, but it's essentially just saying that it's Newton seconds, which is our units that we have for linear momentum, and then this position vector is going to have a length measurement. So Newton second meters would be another way to look at this. And of course, we know that linear momentum is the mass of the particle multiplied times the inertial velocity. And so angular momentum, h, as observed in the inertial reference frame of point P with respect to point O, or about point O, is equal to this lever arm crossed with the mass of point P multiplied times the velocity of P with respect to point O, as observed in the inertial reference frame. And so this is a vector. The same way that linear momentum is a vector, angular momentum is a vector. And the direction of this, you can see, is going to be, because we're in planar motion, let's say that the vectors, our position vector and then our velocity vector, because it's planar motion, if we're in the inertial reference basis, the basis of the inertial reference frame, which is E1, E2, E3, then what we've got is a cross product of something made up of E1 and E2 with something that's made up of E1 and E2. And that's going to give us a vector that's pointed in the E3 direction. So in planar problems, our angular momentum, this h of mass P with respect to point O as observed in the inertial reference frame, is always going to be in the E3 direction, or in the negative E3 direction, and we'll let the scalar tell us that. Next, let's demonstrate why it's important to indicate at what point that you're calculating the angular momentum about. So here, the inertial point that we're choosing, this fixed point that we're choosing, matters. And what's implied here is that we should get a different value of angular momentum depending on the inertial point that we choose to calculate this about. So let's find the angular momentum about point O of this simple pendulum, as well as about point Q of this same simple pendulum, and see what we come up with. So the angular momentum of point P with respect to point O, observe the inertial reference frame. Using our definition, this is equal to R, P with respect to O, cross with the mass of at point P, crossed with, or mass of point P multiplied times the velocity of p as observed in the inertial reference frame. And so just like any other problem, we need to work on our kinematics. So first we define our position vector, and that's r, p with respect to o, is going to be equal to, in this problem, we have our inertial reference frame in the E1, E2, and then we have our polar frame in ER, E theta. And so our position vector is simply going to be L in the ER direction, and then we can take the time differentiation of this in the inertial reference frame to get our velocity as observed in the inertial reference frame, which is L theta dot in the E theta direction. And we've derived this many times. And so we get our velocity, and so plug this back in. So our angular momentum of point P relative to point O in the inertial reference frame is going to be our position, which is L in the ER direction, cross with the mass of point P times the velocity, L theta dot, in the E theta direction. And so what we get here is going to be the expression, the mass times L squared theta dot in the EZ direction. Okay, so EZ is in our polar frame. That's our third basis vector in the polar frame, and that is in a line with E3 as we've defined our reference frames here. And so here's our expression for our angular momentum about point P about point O, the inertially fixed point O. So let's do the same thing for our angular momentum of point P about the inertially fixed point Q. So now we're calculating our angular momentum of this mass P about point Q. So this is in the inertial reference frame. And so our position vector is going to be r p with respect to Q, cross with our mass times our velocity of P as observed in the inertial reference frame. And so in this case, r of P with respect to Q is going to be this distance d in the E2 direction plus L in the ER direction. And we know that the velocity of point P with respect to Q is equivalent to the velocity of point P with respect to O as observed in the inertial reference frame. So it's L theta dot E theta. And the reason why is because both P and Q are fixed within the inertial reference frame. So therefore, the velocity of the point P, the translational velocity this is going to be the same relative to both of those points. And so to calculate the angular momentum of P with respect to Q in the inertial reference frame, we're going to have our position vector, which is d E sub 2 plus L in the E sub r direction, cross with the mass of point P, L theta dot in the E theta direction. And so we need to, we've got a mix of coordinates here because we've got something in the inertial basis in the E2 direction, then we've got ER and E theta. In this case, it's going to be easiest to convert everything to the polar frame, ER, E theta. And so we have from our transformation table that E2 is equal to sine theta in the ER direction plus cosine theta in the E theta direction. So we make that substitution, and we get that the angular momentum of point P as observed, or at point P relative to Q as observed in the inertial reference frame, is equal to d sine theta plus L in the ER direction. We collect our terms in that basis vector ER plus d cosine theta, E theta direction, cross with the mass of point P, L theta dot, in the E theta direction. And so when we plug through all the algebra, we get that the angular momentum of point P with respect to Q, as observed in the inertial reference frame, is equal to the mass of point P, L squared, theta dot, and then it's going to be the entire quantity of 1 plus d over L sine theta, and that's all in the EZ direction. And so you can see here that this expression actually looks pretty similar to what we have up here of the angular momentum of point P relative to point O, and this is angular momentum of point P relative to point Q, and we see that we get the mass multiplied times the length squared times theta dot in both terms. But instead of only having the angular momentum that's ml squared theta dot, we have more. We have this term d over L sine theta. And so there's this is representing that additional lever arm for the angular momentum. And so this mention of this lever arm, that we talked about, you've got this additional d term from Q to O. This talk of a lever arm may remind you of statics, where we had a lever arm when we were talking about the moment. So another way to express the way that we've written this angular momentum is actually called the moment of momentum. And you see here in the expression where we have our angular momentum is equal to some position vector cross with the momentum, it looks just like a moment because we have r cross something. And that something is not f, because a moment is r cross f, but it's actually r cross momentum. And in fact, this expression is related to the moment. So let's show how that happens. So if we start out with our expression for angular momentum, we use P with respect to O as observed in the inertial reference frame, is equal to, and it's R, P with respect to O, cross with the mass of point P, the velocity of P with respect to O as observed in the inertial reference frame. So let's start with this expression that we have defining angular momentum, and let's take the time derivative of both sides. So we take time derivative, so this is d dt as observed in the inertial reference frame, and then on the other side we'll do the same with the entire quantity. And so this is d dt as observed in the inertial reference frame. And so we'll keep the left-hand side the same. So the time derivative of the inertial reference frame of the angular momentum of P with respect to O as observed in the inertial reference frame. And then to take the time derivative of the right-hand side, we use the chain rule for this cross product. So it's d dt, inertial reference frame, of our position vector, r, P with respect to O, and that's cross with mp of our velocity of P with respect to O. And then for the second half of the chain rule, it'll be our position vector, rp with respect to O, cross with the time derivative of our momentum. So it's mp, or mass of point P, v of point P with respect to O as observed in the inertial reference frame. And so then these terms right here, let's write these out. So d dt, observed in the inertial reference frame of angular momentum, observed in the inertial reference frame, is going to be the velocity, or time derivative of our position vector, the velocity of point P as with respect to point O, as observed in the inertial reference frame, cross with the mass multiplied times v, P with respect to O, as observed in the inertial reference frame. And then our second part is our position vector, rp with respect to O, cross with the mass of the particle multiplied times the time derivative of velocity, which is the acceleration of P with respect to O, as observed in the inertial reference frame. So we can really simplify our life quite a bit here, because we know that a vector v of P with respect to O, cross with itself gives us 0 every time. And in addition to that, if we look at this next term, we've got r, our position vector, cross with the mass times acceleration. And mass times acceleration according to Newton's second law, is the force, all the forces acting on the particle. And so this gives us a nice and neat form of this expression. So it's the time derivative, as observed in the inertial reference frame, of the angular momentum of point P relative to point O, as observed in the inertial reference frame, is equal to, it's Rp with respect to O cross with the forces on point P. These are the external forces. And back to our comment about the moment, we see now that we have R, our position vector, cross with all the external forces on P, or all the forces on P, and this is the moment. The moment of, and here we have to write P with respect to O. And so this gives us a really important finding in which we see that the time derivative, as observed in the inertial reference frame, of the angular momentum of particle P relative to a fixed point, point O, is equal to the moment of the forces acting on P relative to point O. And so what we see here is that this form, this time derivative of angular momentum is equal to the moment, is still Newton's second law. And that's the important piece here, is that this is Newton's second law, but it's in a rotational form. It's in the form of angular momentum. And we're going to see how valuable that is in the next example that we do. And so, in this expression where we have the time derivative of angular momentum is equal to the moment, when the time derivative of the angular momentum is equal to 0, then the moment about O has to be 0 as well. And so what it means when the time derivative of the angular momentum is equal to 0 is we're saying that angular momentum isn't changing. And so when this occurs, when the time derivative of angular momentum is equal to 0, then angular momentum is conserved. And this is similar to the law of conservation that we introduced from Chapter 2, or even in the last lesson, in which linear momentum was conserved when the force is equal to 0. Well, angular momentum is conserved when the moment about that point in which you calculated your angular momentum is 0. And this concept of conservation of angular momentum is very important in a lot of situations. I mean, in fact, it's even this idea of conserving angular momentum is what helps us walk. And that's introduced in tutorial 4.1, in which we're applying this concept of angular momentum and this conservation of angular momentum. In addition, conservation of angular momentum is crucial when considering orbital motion. And so, remember, in orbital motion, where you've got the big mass, and then we've got either a satellite or maybe another planet or a moon, and this is our little mass of point P, then there's a force in between, or a force that's pulling these two objects together, which we call big gravity, and that force is equal to gravitational constant multiplied times the mass of the big mass multiplied times the little mass, and divide that by r squared. And that's where r is simply the distance between the center of mass of each of these masses. And so why angular momentum is important here is because if we calculate angular momentum, let's say about point O, which is in the middle of the Earth, if this is the Earth and then that's a satellite, then we see that the only forces that are acting on both of these objects are in this direction. And so the forces themselves, this gravitational force, is going through the center of mass of both of those objects. And so there is no moment, if we take point O and calculate the moment of all the forces about point O, there is no moment. And so, as this satellite is in its orbit about the Earth, then it's staying in that orbit because we've got a conservation of angular momentum, and no matter what, this gravitational force is always pointed to the center of mass of both objects. So this force, this gravitational force, isn't creating a moment. And if it's not creating a moment, then angular momentum is conserved. Next, let's apply the Newton's second law in that angular momentum form to solve for the equations of motion of a system. And so that expression was the time derivative as observed in the inertial reference frame of the angular momentum of mass p with respect to O as observed in the inertial reference frame is equal to the moment of p with respect to O. And so we need to calculate the left-hand side, we need to calculate the right-hand side. This is the same setup that we had for the earlier example, so we already know that the angular momentum of point P with relative to point O as observed in the inertial reference frame is equal to the mass of point P L squared theta dot, and this is in the EZ direction. And so to finish out the left-hand side, we need to take the time derivative of this quantity, P with respect to O, as observed in the inertial reference frame. And then when we take the time derivative of this, we simply get our constant mass, our constant length, squared. And then when we take the time derivative of theta dot, we get theta double dot, and that's in the EZ direction. And so our left-hand side is complete in this expression. So now we need to calculate the right-hand side. The right-hand side being the moment of the forces acting on point P relative to point O. So for our moment, let's say that P with respect to O, our moment is equal to R of P with respect to O crossed with the forces acting on that particle P, and so that's our moment. And so when we fill this out, M of P with respect to O, our moment, is equal to L in the ER direction, and then this is going to be crossed with all those forces. But we don't have our forces yet. To get our forces, we simply need to draw our free body diagram. So for our free body diagram of this simple pendulum, which we've drawn before many times, it's gravity pointing down, but this is in the not negative direction, but it's in the positive E1 direction. And then we need to add a normal force, and our normal force is going to be pulling on that object, or pulling on the mass, and so this is a minus in the ER direction when pointed back toward O, so from point P to point O. And so let's finish our expression for our moment, where we have L in the ER direction crossed with, it's going to be all these forces, which when we put these in here, negative in the ER direction, plus mg in the E1 direction. Once again, we have the problem in which we have a mixed use of our basis, because ER is in the polar frame, ER is in the polar frame, and then E1 is in the Cartesian frame, in the inertial frame. And so, because we have this information that relates the two frames together, let's take our basis vectors in the inertial frame and convert them to the polar frame. And so that's only one vector, in which we have E1, which is equal to cosine theta ER minus sine theta E theta. Let's make that substitution and expand our cross product. And so we get the moment of P relative to O is equal to L ER cross with, and so negative in the ER direction plus mg cosine theta ER minus mg sine theta in the e theta direction. And so when we distribute our cross products, we get that L in the ER direction cross with minus N in the ER direction is going to be 0. L in the ER direction cross with mg cosine theta in the ER direction is going to be 0, because ER cross ER is equal to 0. And so the only term that comes out of this that we keep is going to be L multiplied times mg sine theta, and this is ER cross with E theta, and so we keep our negative sign from the negative mg sine theta on the right hand side here. ER cross with E theta gives us EZ, and so now we have the moment that would be on the right hand side. And so now that we've got this, we take these two expressions and then we combine our sides. And so let's equate both sides. And so on our left hand side, it's the mass of particle P times L squared times theta double dot in the EZ direction. And then this is equal to negative L mg sine theta, and that's in the positive EZ direction. And so we take our scalars out, we solve for theta double dot, and so we solve for theta double dot, we get the expression theta double dot is equal to minus g over L sine theta. Now, this is a particularly important result because what we've done is we've solved for this simple pendulum. We've gotten an equation of motion that we're familiar with. We recognize this theta double dot is equal to negative g over L sine theta. But notice what we did. We used this form of angular momentum, time derivative of angular momentum is equal to the moment, which is simply just another way of writing F equals ma. F equals ma is buried in this. We can calculate the equations of motion. But more importantly, look at what we had to use and what we didn't have to use here. Notice that in this we only got one equation. In the past, oftentimes what we've gotten is we've gotten two equations where we get an equation that's an equation of motion and the other that's a constraint equation. Because of the way that we set this up, our normal vector was our normal force vector was going through the point in which we were calculating our angular momentum, or our time derivative of angular momentum. And so as a result, we completely eliminated the constraint force. We didn't need it. So that was actually a pretty quick process. That's a great result. However, the bad part about this is that we don't have a constraint force. We don't have an expression for that. We'll have to get that some other way. So it's kind of good and bad. But the other, or in addition to that, the other great thing that comes from this is notice that we used F equals ma. We used the Newton's second law, but in our calculations, we only had to calculate the inertial velocity to solve this problem. We never, not once, had to calculate the inertial acceleration. Because if we look back at when we calculated the angular momentum of point P with respect to O, it's all based on a position vector and a velocity vector to be able to get this expression, the mass of point P multiplied times L squared times theta dot. So no acceleration there. And then when we plug all this in, take the time derivative, we simply have to take the time derivative of this expression, which is not acceleration, and then find our moment. So we never really had to calculate acceleration in this example, which is actually kind of lends itself to some of the more advanced methods that you would see in graduate school, where we're calculating using Lagrange's methods or Hamiltonians. We never ever have to calculate acceleration. So that's really a nice finding. We can get this equation of motion, one, by ignoring constraint forces because they didn't show up in our formulation here, but then also we never had to calculate anything beyond the inertial velocity of that particle. And so that wraps up our idea of angular momentum about an inertially fixed point. In lesson 14, we're going to introduce the angular momentum about a point that's not inertially fixed. So angular momentum about a point that's moving, and this expands the usefulness of this equation of angular momentum, or of calculating equations of motion using this form. All right, I'll see you in class.